everybody. I'm sorry that I can't be with you today for to go over the lesson 6 lab on elasticity, but thank you so much for watching the recording, and I'm hoping that this will help you understand how to complete the 5.06 lab. And just a reminder, this lab is a 2-day lab, so you will have Monday and Tuesday. If you look at the course calendar, you'll have both of those days actually to complete this. So use your time wisely, but know that you're not going to have to rush through this. So you'll have all day Monday, and then it says that it's a different lesson in lab at Elasticity 2, but if you click it, it's actually going to be the exact same lab, so you won't really have to worry about completing the lab again. See, it says if you did not finish the lab in the previous lesson, do so now. Okay, so I'm going to start going over just some of the goals of the lab, and you might want to have out the student guide and also the graded assignment while you're listening to this, because you may actually be able to get a lot of it filled out as you're listening to this recording. So the goals for this are going to be using the scientific method to solve a problem. We will also be using the metric system to make some measurements during our lab. And then the specific goal for this lab is to determine how elastic objects respond to force by stretching rubber bands that have different masses to them. So if you're using your graded assignment right now, that is really, if you look at question number 1 that says write the goal of the lab or the question you tried to answer, saying this right here, how do elastic objects respond to force by stretching rubber bands that have different masses? That is exactly the goal and your answer to question number 1 right there. And that's kind of a good key right here, is almost all of your labs are going to have this goal for the lesson down here, and usually the last bullet point is pretty much exactly what you can write in your own words, of course, for question number 1 when it's asking you the goal of a lab. So please read this on your own. Just know that what force is, and then you'll also need to know what elasticity is. So when you're going to do this on your own, then please make sure you're reading this. Again, here's where you're going to download the student guide. Make sure you've done that. And always, so I'm going to pull the student guide up really quick. And you always want to make sure that you're referring to this before you even start a lab. You can see right up here is your goal again. Here's your answer to question number 1, the materials that you'll need, and then the key part is the procedure down here. That's really what's going to show you what you need to do in the lab. So we're going to look at a video of an elasticity experiment, and then you'll be given experimental data to fill out your own lab report with, and that experimental data is down here. So all that you'll need to do is you're going to copy pretty much all of these numbers from these tables into your graded assignment, and then you'll have to calculate the change in length in centimeters by subtracting. Okay. And then have the data in front of you, of course, as you're completing your lab report. So the procedures for this lab are pretty simple. I'm going to pull up what the lab report looks like here. It's called the Physical Science Elasticity Lab Report Graded Assignment. And again, I just got this right off of the LMS. So the goal for this lab, again, that was just coming off of the first page of the lab, and it's also found as the last bullet point on top of your student guide, so refer to that. Here, just a reminder, the observations, experiences, or lesson materials that helped you form your hypothesis. So remember, a hypothesis is an educated guess. So if it's an educated guess, I want to think about what are some experiences with elasticity that I already have that are going to help me decide on what I think is going to happen in this lab. So I know that I have used rubber bands before, and sometimes a rubber band will break if I use one that's too skinny. So sometimes I have to use a thicker one, but if I'm trying to put that around a larger object, sometimes it's more difficult because it's not quite as elastic. So those are just some different observations and experiences I've personally had in the past that may help me make my hypothesis. So this is not listing materials or anything like that. This is just your previous experiences with the goal or question you're trying to answer that are going to help you make an if, then, because statement based on some sort of prior knowledge that you have so that it's not a random guess. Okay, so we are going to watch this lab video, and as we're watching it, please have your lab report out, the graded assignment, and you can really be filling a lot of this in as we're watching the lab.
Hi, I'm Pat Keeney, an instructional designer with K-12. I'm here with my assistant to help you explore elasticity. In most lab work, advanced preparation is needed, and safety is always important to consider. If you stretch a rubber band, what happens to it when you let it go? The rubber band returns to its original shape, of course. But if you stretch clay and let it go, what happens? It remains stretched or deformed. The rubber band has more elasticity than clay. That is, the rubber band goes back to the shape it was before.
So I'm going to pause that. Right here is some great prior knowledge or experiences or observations and lesson materials that you could just put into your own words for question number 2.
If a solid recovers its shape after being pulled, pushed, or stretched, it is said to be elastic. Springs, bungee cords, and rubber bands all have elasticity. The important question to consider in this lab is, how do elastic objects behave when different forces are applied?
So I'm going to go back to this. So that was also, so question 1 is asking you, what is the goal of the lab, or what is the question you tried to answer? So he just gave you guys right here, how do elastic objects react to forces? That, if you rather put that for question 1, then you are more than welcome to do that. Or you can use the goal of the lab that we discussed before from the student guide. Either one.
Elastic objects behave when different forces are applied. Use your prior knowledge to write a hypothesis that describes how a rubber band might respond to different forces. A good hypothesis should take the form of an if-then statement, such as, if a greater force is applied to a rubber band, then the answer may seem obvious, but how would we confirm this?
Okay, so this is a main point that I want to highlight here because a lot of students have been losing points for not putting their hypothesis for question 3 in the proper format. So you want to make sure you're always writing an if, then, because statement. So like he said, if an object is more elastic, then it will stretch further. And that would be a good example of a hypothesis. You want it to say if blank happens, then blank is going to happen.
Here are the materials for the lab. Before starting the procedure, we created a table with the following columns: original length in centimeters, mass in grams, length with mass attached in centimeters, and change in length in centimeters. Now it's time to set up. We can secure a dowel rod with a length of string attached to the edge of a countertop using tape. The dowel rod is secure and stable. There are more than 50 centimeters between the dowel rod and the floor. This space is needed for the stretching of the rubber band. We then tied a ring hook to the free end of the string. We measure the length of the hanging rubber band and record this value as the original length in the data table. Next, we attach the 100-gram mass and record this value in the data table. We hang the hooked mass on the free end of the rubber band. Again, we measure the length, this time with the mass attached, and record this value in the data table. We did a series of these experiments, and in each case, recorded data with different masses attached and with different rubber bands. The differences in lengths are easily calculated and recorded. Consider how the results should best be analyzed. You will be given data to work with.
Okay, so I'm going to stop that here. So again, you are going to get lots of, we're going to go over this line of best fit thing in 1 second, but You are given the data, and the data can be found in the student guide, and you're going to use that data to fill in this table. So in the student guide, you got 3 different tables. So you are going to need to now use what you know about tables to take this information. I'm going to try to bring it over here so you can see both of them on the screen at the same time, so that you can take this information from 3 tables and smush it into one. So you can see here, type of rubber band, thin, medium, and thick. And it tells you up here, this table has to do with the thin rubber band. This is the common rubber band, which would be medium. So common is going to go under medium. And then the thick rubber band's data is here. So that'll go under thick. So it asks you all of these questions that, again, your student guide has for you, such as the original length, the mass, and the length with mass attached. So all of these things are found right here. And so then the change in the mass is going to be the difference between this number, the difference between this number, the original length, and how much it changed. So how much did it stretch out when it had weight added to it. Okay, so you're subtracting the original length from the length of the mass when it was attached to find out how much it stretched. And then you're going to plot your data. No one seems to be having trouble with this from the lab reports I've been grading lately. You seem to have this down now, so keep that up, plotting this data. You're going to put, as you can see here, our dependent variable is the length of the rubber band, and our independent variable is the mass in grams. So if I go up here, I'm going to look at the stretch length. That's what's going to go on my my y-axis, stretch length, right here. Okay, and then the mass in grams, which will be here, that's going to go on my x-axis because that is my independent variable. Then let me know if your data agreed with your hypothesis. So were you right, were you wrong, and explain your answer. Please don't forget to do that to get all of your credit. And then I wanted to talk quickly about a trend line here. So all a trend line is, you'll have to draw that, is if you look at your data, say this is different data, but here you can see all of these yellow dots were plotted on this graph. And you can find what we call sometimes a line of best fit or a trend line. You can see there's a common trend that these our yellow dots seem to be going in this direction. So to draw a line of best fit, you're going to just insert a line into your graph that you drew and draw it so that it's kind of going through all of your data points and shows the trend that's happening, what direction they're moving in. So that's all that you need to do for that question down here that says draw a trend line that characterizes the data. And then use your graph to predict the thick rubber band's length at 40 grams mass attached to it, or I'm sorry, 400 grams. So your data is only going to go up to 300. So let's say, I'm just making this up, don't copy this. Let's say your line looked something like this. Then you would be able to see, okay, if the data is moving in this direction, then at 400, if I move up, where do I hit? Oh, I hit right around 18 centimeters. So you can predict based on this line, the trend line, where the data is going to be, even though you haven't measured the mass at 400 grams. This will kind of give you an idea of that. So that is all for today. If you have any questions, please send me a K-mail. Again, I will be at a conference, so I may be a little slower answering K-mails than normal, but I will still get back to you within 24 hours. So if you have questions, please ask. Just a reminder, this is due on Tuesday, the 28th. So I would suggest starting it on Monday so that if you do end up having questions, you can K-mail me Monday with your questions and I can get back to you by Tuesday so that you can finish up working on your lab. So good luck with this. Have a wonderful weekend, and I look forward to seeing you guys again on next Tuesday.